So coming back in after someone mysteriously let the time run out, um, when we think about the thermodynamics, iodination is going to be positive delta H, so it's not spontaneous. So this is not thermodynamically favorable, and we don't see it happen. Now, on the other end of that, if you notice when we do our fluorination, our delta H is extremely large. And so what happens is that this is just so reactive, we're never going to see this. It's just violently reactive. It's not a very good thing to use. So in reality, our halogenation products are only ever going to be chlorine and bromine. Those are the only two halogenation reactions we can do. So if you ever see a reaction like this where it says, what's the product of this and F2 or this and I2, you're going to write what? No reaction. Just because one is too spontaneous, one is not spontaneous at all. So when we look here, both chlorination and bromination are exothermic, they're favored. So we are going to form our product, right? So we see here that at the end of the day, we get our products formed. And now we have chlorine at negative 117 and bromine at negative 50. And this is good. This is in the range that we can use this as a practical application. It makes it possible to do this reaction. All right. So now this is actually going to give us a weird little effect that is very useful for us. Bromine is much slower than chlorination. So if I think about, remember the rate of my reaction is this activation energy, right? It's how long it takes to go over that hump for the reaction to occur. So in step one, right, you have your, basically your abstraction, right? And then you have the second step. So when we think about this with chlorination, it proceeds at a much quicker rate, right? It's not too bad. Bromination, though, has a much higher activation energy. So it's a lot slower. But because of this, we're going to see something that's really useful. So now we're going to be able to be regioselective. So do you remember what regioselective is? Stereoselective is when you get a certain stereo product, right? Like cis, trans, or other stuff like that. Chemioselective is when you react with certain chemical groups. Regioselective is when you react with certain types of carbons. So like primary, secondary, tertiary, and stuff like that. So with substrates more complex than ethane, so when we start getting into propane and other things like that, multiple monohalogenation products are possible. So see here, we have propane, right? So we have these here and these here. So when I do a halogenation like Cl2, which one is going to be replaced, Gwen?
The hydrogen?
But which one? One of the yellow ones or one of the green ones? They're different.
The yellow ones?
Maybe. So this is just it though, is that when we do these halogenations now, they become selective. And so when we start introducing more complex systems and we're doing halogenations, you're going to have certain regioselectivity, meaning your halogens are going to prefer to go to certain carbons. So Gwen, you are technically right. What type of carbon is this one here? How many carbons is it attached to?
Secondary.
It's a secondary carbon, and these are what? On the outside. They're primary.
Oh, I didn't know. I wasn't sure if that's what you were asking. I'm sorry.
That's right. So you have primary here and secondary. What we find is that when you do halogenation with chlorine, they prefer the secondary carbons, and then they prefer tertiary even more. But Mag, if you could give me a hand here, what's the only problem with that logic? Because they do prefer these hydrogens here, right, more than these. But what else are we taking into consideration?
Those are like the least stable ones.
Kind of.
Yeah, that's my only guess.
Okay. So we said that when we do this halogenation, they prefer these ones here, right? But how many hydrogens are there altogether? There are 8 of them, right? So it becomes a probability game. Even though it prefers these two, there's more of these, so they may also come into play because it's just a numbers game. Okay. Does that make sense?
And does it also have something to do with the fact that it's in this particular slide, it's like talking about chlorine, so it's not very like selective, I guess.
Yes, chlorine is the hussy of the halogen group. But I don't slut shame. It's just, sometimes you need to take home a carbon group, and this is what this halogen shows. I'm not going to judge. It's not tertiary carbon. That's fine. Sometimes you have to take home a methyl or a primary. No, so chlorine, as we saw, right? Remember looking back at this reaction, how high was that activation energy for chlorine? Not that high, right? It doesn't need a lot to make that happen. This is why chlorine isn't that selective. Bromine, though, has this very huge activation energy. So what we're going to see with bromine is much more selective. So now as we scroll down, when we look at this, our halogenation reaction, right? So here I have my secondary in the middle and my primary on the outside. So my chlorine could either add to the secondary carbon or to one of the two primaries, right? And so 60% of the time, it is going to add to our secondary. 40% of the time, it is going to add to our primary. I don't know why bromine standards are impossible. Well, it's good to have standards, but sometimes you need to just sweep them under the rug. And I have to say, as a guy, I'm very appreciative of every woman that has ever swept her standards under the rug. A big fan of all of those women for lowering their standards. Very happy. It's called being a team player. But you can see here that we see the difference in energy, right? It's because, like I think Max said, is that when we form our secondary radical versus our primary, secondaries are more stable, right? This is why the secondary carbon is going to form more readily. And then if we had a tertiary carbon, that would form even more readily, right? But the issue then becomes is that since there's very little difference, the number of hydrogens start coming into play, right? So the chlorine can replace one of two hydrogens here or one of six hydrogens on the outside. So it's a numbers game of which one is favored versus how many opportunities there are, right? However, coming into bromine now, bromine is much slower. And so what's going to happen is that bromine is extremely regioselective, meaning that bromine is going to prefer the most substituted carbon every time. Every time. You will not get a mix of products. All right. So when we come here, we're going to take a quick look and we're going to talk about something called the Hammond postulate. Have you guys talked about the Hammond postulate? Okay. Well, this is your take a note because you will have a question. The Hammond postulate says that so here's my transition state, right? So what is closer to my transition state, the reactants or the products?
Reactants.
So my transition state, is it going to more closely resemble my reactants or my intermediates?
Reactants.
Reactants, all right? Now on this one, here's my transition state. Is it closer in energy to my intermediates or to my reactants?
Intermediates.
So which one is it going to more closely resemble?
The intermediates.
Okay, does that make sense for the Hammond postulate? Essentially, it just says whatever thing my transition state is closer to an energy, meaning what is closer to it on this graph, it's going to resemble that more than it will the other thing. All right, so the bromination transition state resembles the products. The chlorination transition state resembles the reactants. All right. So now, when I come here and I think about this, essentially what this means is that as this reaction goes, we're going to see that bromine is going to be extremely more selective than chlorine is going to be. All right, so chlorine is more like this on the left side, bromine is more like this on the right side, right? So this is just something to remember because you will get a question that says, what is the Hammond postulate? I guarantee you will have that question. We will come across it again. All right. So now, for bromination, the stability of the transition state largely depends on the stability of the resulting carbon, right? So when we think about transition states, since the transition state looks more like our intermediate, it's going to want to have more stability. So because of this, bromine is going to really, really want to be attached to a higher order carbon. So in chlorine, if we look here at the chlorine radical, right, primary versus secondary versus tertiary, those energy levels are very close together. This is why if I give you a compound and I say, what are all the possible products? In fact, we're going to do that right now. This will be a good test for you. I'm going to give you, so here is this. I want you to give me all the products for this reaction. All right. There are your 4 products. It looks like there should be 5, but those 2 are the same. Did you guys get those 4? Essentially, you can add a chlorine to this carbon, right, which is going to be this one. You can add a chlorine to this carbon, which is going to be this one. You can add a chlorine to this carbon, which is going to be this one. And then if you add one to here or here, it's going to give you these 2. They're essentially the same thing. Does that make sense, though, on how you can add chlorination products? All right, so now, before we get to the next step, if I redo this again, draw me all the products for this reaction.
Wouldn't you just get one?
I don't know. That's why I asked you the question. There's your only product. Because bromine is so selective as opposed to chlorine, it will always brominate your your highest ordered carbon. So tertiary would always be formed, right? So you're only ever going to get this one product. The other ones will not form. Does that make sense? Okay. Let's go back to our. Okay. So now if you look here at this halogen regioselectivity, right? This is why if we look here at our activation energy, look how much higher primary is to secondary to tertiary. So the tertiary activation energy for our free radical reactions is so much lower. This is why we get this difference in selectivity. Bromine is always going to take the highest ordered carbon all day, every day. All right. So when we look at our bromination, so bromination at a tertiary position is 1,600 times more likely than at a primary carbon. This is how much more favorable it is. All right, so if you think this now on the right side, this is the relative rate for fluorination, for chlorination, and then for bromination. So bromination happens so readily that a secondary carbon is 82 times more reactive than a primary, and a tertiary is 1600 more times reactive than a primary. And so then that's going to be about what, 20 more times, no, yeah, 20 more times selective than the secondary, right? So this is why tertiary carbons. So if you had a reaction and you wanted to add a bromine to one specific carbon, right, and it's the tertiary carbon that you want to add to, like you want a halogen there, that's the one you use. If you need it to go to a different one, like you need a chlorine to go to someplace, then that's when you use chlorine, right? Chlorine will go everywhere. Bromine only goes to one place. So radical halogenation reactions using blank are the most reactive and often lead to multiple products, while radical halogenation reactants using blank are the most blank and produce primarily the major product. So which of these is the correct letters?
D.
What'd you say? D?
D.
B as in boy?
No, D.
D as in doy?
Yes.
Dog. Yeah. Radical halogenation using chlorine are the most reactive and often lead to multiple products, correct? Why radical halogenation reactions using bromine are the most selective and produce primarily the major product. Yep, that's correct. All right, so what is the major product of the following reaction?
A.
A is correct. That is going to be our most selective one. So that sounds reasonable. So how are you guys feeling about this? Better? All right. Let me just take a look here real quick at what's all. I'm going to say let's call it a break here for tonight because I have to go write a test. But I can meet on Saturday to record the video. So if you guys want to show up, I can do the second half of this. If not, then don't worry about it. I want to say I want to do it just a little bit earlier because I have some stuff to do that day, like sleeping. So are you guys, I'll do it at 4 your time. So if you're not available, I'll still record it. So I'll just label these videos will be radical halogenation part 1, and then the next ones will be radical halogenations part 2. So then that way they just go in order. So any questions before I go? Or are you all good?
Yeah, I think this has been very helpful, actually.
Okay, hopefully
I
this,
feel better.
all right. And you have the NMR test coming out, right?
Yeah.
Yes.
There's an NMR packet that I can send to you.
All right. Next week we can work on that because we'll finish this halogenation stuff, and next week we're gonna work on the NMR stuff. What other new topics are you working on?
I think that's all that we're doing.
Yeah. Yeah, I
Just
think
the
we're gonna do NMR, and then I think she said we're just kind of gonna review stuff like after that.
Okay, so we can do NMR next week, and then we can review the following week, and then we'll meet the weekend before your final exam since it's on a Monday.
Okay.
And then you guys will be free for the summer.
There-
In sad news, NAU, the summer program is not